Hello, class. Can you hear me?
Yes po.
Yes po.
But you can't see me. May problema yung aking laptop ngayon. Teka lang ha, ngayon ko lang na-discover kasi. Ayun. Yun pala yun. Akala ko may problema ako, anak. Wait lang. Okay, good to see you everyone. So today, we will have a lecture first before we conduct our next experiment. Uh, the next topic, allow me to share with you our module so that you will be on board with me. Wait lang, anak. So, okay, class. So, the second topic is about buffer effects on solution and also calculation calculation of computation of the pH of of unbuffered solution and buffered solution. So this will be the ones that we will be discussing today. Okay, and you will be doing at home the effects of temperature on buffer solution. These are our activities for today. Then this topic about the cell, module number 3, is also a lecture activity. If we can finish it today, much better. Okay? Then we will perform our lab experiment 2 on Wednesday. Okay? Then on, naku, Valentine's yon. Maybe, because on Wednesday also will be the submission of your lab report. So, for Wednesday, we will be doing experiment 2. And then next Monday, we will be doing our experiment on the reactions of carbohydrate. And on Wednesday, specific reaction that will be laboratory experiment 3 and laboratory experiment 4. Then after that, we will be performing our experiments on lipids the week after that, and then the experiment on amino acid. So that's it. And those will be the topic for the midterms examination up to the experiment on amino acid. So laboratory experiment number 7. I want you to be with me with regards to the topic that we will be discussing, so that you can read in advance uh, the experiment that we will be doing, the concepts behind that. Okay, so we will be all ready for the coming weeks. Okay ba, anak? So yun, hanggang module 7 tayo. For you will have those are the topics for the midterms examination. I will just look back into the recommended table. Hanggang lipids lang pala. mapapasobra pa ako. So, hanggang lipids lang, experiment number 6. And experiment number 7, proteins will be included for the, okay, so that we will have enough time to review. I think that will be good for us. We have enough time. And if ever, so, okay, so our midterm examination is up to lipids only. And then I'll go back to the module. Up to experiment 6. Okay. Experiment 7 and experiment number 8, 9, and the last experiment I think is experiment number 11, urine experiment. Those are for our finals. Okay, if ever we finish earlier the experiment class, I think tuloy-tuloy lang tayo hanggang para hindi pasayang yung ating klase. Para doon na lang tayo sa pahuli magkakaroon ng uh, online classes after this. Okay? Kasi ito lecture din itong blood. At yung nucleic acid, a part of it also is lecture. Okay, so let's start with uh, calculation of pH in buffered and unbuffered solution. Okay, class. For the first experiment, what did you notice is the change in pH of an unbuffered solution. When you add hydrochloric acid to your water, what is the change in pH? Anyone? What is the change in pH when we add hydrochloric acid in water? Do you have your data with you? Wala. Walang nasagot sa akin. Okay. Anyone? You may use the chat box if you like. No change po, according to Aliyah. Okay, so for Aliyah, it's no change. How about the other groups? What did you notice? Wait lang. About the pH. Okay. When we add water, when we add acid to water class, there is a drastic change in pH. Okay? It will immediately go down below 7. Okay. According to Michaela, it lowers down the value of the pH. That's true. So for example, I'll write here, the pH of our solution in water has a pH of 7. If you add, how many drops, how many ml of hydrochloric acid did you add, and what is the normality or molarity of the hydrochloric acid that we add? Sige nga, let's. Okay. So how we place 0.1 ml of 1 molar hydrochloric acid. Okay, class. So that is the amount of hydrochloric acid that we add. So it lowers down the pH of our solution. Okay, it drastically lowers the pH of the solution. From 7, it may go down to, yeah, thank you. From 7, it may go down to 6, or it may go from 7, it may lower down the pH to 5 below. Okay? So, sabi ko, o sige, wag na nating baguhin yung data kung hindi nag-lower yung pH. Aliyah, you mentioned that there is no change in pH. If ever that happens, where is that, why is it that your result did not follow the trend of pH lowering when acid is added? Why is it that the solution did not lower its pH when the acid is added? What do you think is the problem? Saan galing yung error natin, anak? Sa palagay mo lang. Okay, pwede. May nahalong ibang solution sa tube na ginamit. Okay, class. This is one interesting observation that we have. The pH of the distilled water is what? What is the pH of our distilled water? Anyone from the group? Have you observed that one? The pH is? Yes, Miss Kahapin.
7
7?
po.
7 ba?
Yes
7 ba,
po.
anak? Okay, buti pa. Sino yung, yan, o yan o. Ang dami kasing group na ang pH ay hindi 7. Ang pH nila ay 5. So I expect that there might be some contamination that happened somewhere along the way. So the distilled water itself is contaminated. Okay? So that's why the observation is not very conclusive. Okay? So we have some errors uh, in the experiment. Okay. So isa 'yun sa nakita natin na parang may mali. Saan ba ang mali? Kaya lang hindi na tayo nagpalit ng distilled water. Kasi even yung nasa wash bottle, masyado din siyang acidic. So, nakakapagtaka yun. Okay. Now, sige. So, nasettle natin yon. Alam natin kung yung error natin sa first part ng experiment. Now, when you add the base in your pure water, what happened to the pH naman? It, anyone from the group? Rain. Rain, what did you observe when we add base in our distilled water?
For our group po, ano po, mali po yung results namin.
Okay lang, kahit mali. Okay lang, kahit mali yung result. It's okay. Just mention to us what happened to the pH of your distilled. Kasi constant yun sa inyo, di ba, Rain? Parang constant lahat yun sa inyo sa distilled water. Tama ba? Rain? Kasi
Um,
nakita ko,
ano po,
constant yun sa inyo dun sa distilled water.
yes
555
po.
yun. Ayun,
Constant po
oo.
or little change lang po yung sa pH.
Oo nga. So again, there is something wrong in our solution. Uh, I ask you naman to bring your own and use your own pipettes, di ba? Or maybe what really have been issued to us is really contaminated. Yun na lang talaga. Pero, what do we expect, Rain? Okay, given that you have that result, so theoretically, what will happen to the pH of the solution if you add sodium hydroxide? Anyone from the group? What will happen to the pH of the solution? It, if you add a base, it will decrease according to Miss Castillo, or it will, sinulat ko sa board, it will increase. Okay. So, it will increase. So, wait lang anak. So, in an unbuffered solution, when we add a base, it will increase the pH drastically. And if we add an acid, the pH will be decreased. Okay? Now, if it is a buffered solution, the pH will not change abruptly. There will be some constancy in the pH if you add a strong acid or a strong base. Okay? So, those are important things to remember. Now, goodbye, ma'am. Bye. If you add, now, if it is an unbuffered solution, the pH will decrease if you add an acid, and the pH will increase if you add a base. Okay, I hope that is clear for us. Okay? Wait lang, anak. Hello. Bye. Okay. Wait. So if you add acid to the buffer solution, no change in pH. Okay. So if you add an acid to an unbuffered solution, there will be a decrease in pH. Now, if you add a base to a buffer solution, there will also be no change in pH. And if you add a base to an unbuffered solution, what you will have is an increase in pH. Okay? I hope this relationship is clear to all of you. Now, why is it very important again to have a buffer solution in biological system? Okay. Why is it important to have a buffer system for uh, biological organism? Do you still remember? For example, in our mouth, we have salivary amylase. And what is the desired pH of the salivary amylase? Do you still remember? Okay, very good, Carmela. Because that way po, the body will work properly like in the blood. Very good. That's a good answer. Okay. How will the body will work properly? For example, in our mouth. So in our mouth, we have an enzyme known as salivary amylase. Okay. So, which work best at pH 7. Now, what will happen to the enzyme if we eat or if we drink for example, Pepsi Cola? What will happen to the pH of our mouth if we eat Pepsi Cola? What is the pH of Pepsi Cola? The pH is almost 2.5, right? Okay. So, so which so the okay, the pH of Pepsi Cola is 2.5. So what will happen to the enzyme? Will it work properly or not? Will it work properly or not, anak? Oh, you drink Pepsi Cola? Palagay mo magiging effective ba, anak? Oh, Siyempre, hindi no po. Yan, very good, anak. It will not be very effective. Kasi, uh, the pH of the enzyme is not at its optimum. Kaya nga, sa 'di ba na-mention ko na to last meeting na it is better to drink water during meals than to drink cola or soda because the digestion will not be as effective if we drink water. Okay? Kasi gusto ng ating salivary amylase yung pH na 7. Okay ba? Okay yon. So mahalaga yung ideal pH for optimum activity of the enzyme. I hope that is clear. So let's continue. So the next one is the effect of pH on the effect of um okay. Uwi na kayo. Madala ko ng trabaho. Review tayo. Ano na ako magdala ng trabaho. Okay, I gave this assignment to you. You will make a graph comparing pH and temperature. Okay, so in this graph, you should be able to know the effect of temperature on the pH of a solution. So, now, So in your graph, what do you think should be in the x-axis, anak? What should be written in the x-axis? Okay, so you will write on the x, yung pa-horizontal class, you will write the 0, the 25, the 50, and the 100. Okay? So on the y-axis, you need to write the pH of the solution. Okay? So, you may number it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Pwedeng hanggang ganon. Pero hanggang 7 lang naman. O, pwedeng gawin mo 2, 4, 6, 8. Okay? Then, you know how to make a graph, class? You know how to make a graph? Yes. So, you will make a graph out of this data and then answer the question, what can you say about the relationship between pH and temperature? So what do you think is the trend? What happens to the pH as the temperature gets higher, as the temperature gets lower? Okay? So you have until 12 midnight to answer that this activity in our module. You will submit it here in our module also. So this will not be a group activity but an individual activity. So I will give you time later to make this one. Okay? So I will dismiss you at about 3:30 to be able to make this graph. So now, let's proceed to the computation of the pH of unbuffered solution. So how do we compute for the pH of an unbuffered solution? So, okay. Buti na major may overtime payment. Wala na ba? Lapit na. Alam ko may memo na yun ni... Diba sinabi ni Sarah? Ay, ayun. Okay, so let's look here first for the calculation of the pH of a buffer solution. So in our problem, it is written that a buffer solution is made from 0.1 mole per decimeter of ethanoic acid and 0.2 mole per decimeter of sodium ethanoate. Okay, so calculate the pH of this buffer solution. If the Ka for ethanoic acid is 1.7 times 10 to the minus 5 mole per decimeter at 298 Kelvin. So, what do we need to know? We need first to write the expression for the Ka. HA is equal to H plus A minus. So, this one is our acid in the reactant and this is our hydronium ion together with the conjugate base. Okay? So, that's how you write it. Then, our Ka is equal to H plus aqueous multiply by A minus aqueous divided by HA aqueous. So this is the solubility constant for your acid. Okay? Then so once you have written that, this one, this Ka, so we will make an assumption. So the initial assumption is that all of the A minus comes from the salt. Okay? And almost all of the acidic molecules will remain unchanged. Okay? So this one will now be HA aqueous and salt aqueous and acid over the acid. So we will now put the values given in the expression to find HA. Okay, so we have 1.7 times 10 to the minus 5 is equal to the concentration of our acid is 0.1. The concentration of our conjugate base is 0.2. Diba? So to compute for that, we will multiply 1.7 times 10 to minus 5 with 0.1 and then divide it by 2. That's why we get this one. Okay, and we get 8.5 times 10 to the minus 6 mole per decimeter. Okay, and then we will get the value class is 8.5 times 10 to the minus 6. And we will get negative log of that, which is negative log 8.5 times 10 to the minus 6, and that will be the pH is 5.07 at 298 Kelvin. Hindi ito fun. So this is not really fun. Medyo mahirap to, class. So bakit natin kinuha, bakit ginamit tong equation na to? Kasi ito yung equation para makuha mo ang concentration ng pH. pH is equal to negative log H3O plus. Yun yung isa sa una nyo dapat ma-remember. Okay? pH is equal to negative log H3O plus. Okay? So, okay. Ang dami kasi ditong anak. Ang daming equation. Pero, sandali lang. Okay. Okay. So, isa sa dapat nating malaman nga, sabi ko, pH is equal to negative log of H3O plus. Okay, for example, the concentration of H3O plus is equal to 1 times 10 to the negative 1. Okay? So, the concentration is of H3O plus is 1 times 10 to the negative 1. Okay. Pwede po bang pakigamit ang inyong calculator? Pakikuha yung negative log of H3O plus. So, isa-substitute natin. Gamitin ang inyong mga calculator, ha? So, therefore, pH is equal to negative log of 1 times 10 to the negative 1. Okay. So, what is the pH of this solution? Class, pakitingin sa inyong logarithmic, use the logarithmic function in your calculator. What is this value? Ano nakuha nyo? Na-compute nyo na ba? O sige, papipiliin ko na lang kayo. Plus 1 or negative 1? 1 po. Very good, Aliyah. So, yan. So, ibig sabihin, pag yan ang pH, ganun pala mag-compute ng pH. Diba? Madali lang. So, let's try another one. Paano ko yung pH natin ay another example? Sige. Try to compute. For our next example, let's say it is 10. What is the pH? What will be the pH of this one? Class. Concentration of H2O plus is 1 times 10 to the negative 10. What will be the pH? Sige nga. So, isulat ko ang equation. Control C. What will be the pH of this solution? May sagot na po? Yan, very good. Ang galing nyo naman. Positive 10. Ngayon. Tama yan, anak. So, madali lang pag 1, di ba? And to the base 10. Kasi kung ano yung exponent, yun ang magiging pH ng solution. Okay. So, let us watch a video. how to get the pH of solution that is not on how to get the pH of a solution. So at least alam nyo, to the base 10, madali lang hanapin. Pero paano pag hindi siya, meron pang ibang number aside from 1. Okay, so let us watch now how to calculate the pH and pOH of a solution. Okay?
moles per liter. So I want you to be familiar with some common equations and how to use them. The first formula you need to know is that the pH is equal to negative log of the hydronium ion concentration. Now, before you use a calculator, what do you think the pH is going to be if you had to estimate a range for it? What would you say?
4 plus pH log
Now,
2.
the first number you should look at is the exponent, negative 4. The pH is going to be close to 4. Now, do you think it's going to be 3 to 4 or somewhere between 4 to 5? If this number here is greater than 1, choose the lower region. If it's less than 1, let's say if it was like 0.4 times 10 to the minus 4, I would choose this value. So we know it's somewhere between 3 to 4. Now let's go ahead and plug it in and see what the exact value is. So if we type in negative log 2.5 times 10 to the minus 4, this will give us a pH value of 3.6, which is indeed between 3 to 4. So that's how you can get like a ballpark answer just by looking at this if you don't have access to a calculator. Now let's see what the pH of this solution would be. So if we type in negative log 0.4 times 10 to the minus 4, that will give you a value of 4.4, which is between 4 and 5. Number 2, the pOH of the solution is 4.5. Calculate the pH of the solution. So that's another simple question. What formula do we need in order to calculate the pH given the pOH? So here's the next equation that you want to write. You should add it to your list of equations.
Okay, class. Balikan ko lang yung una, ha? So, bakit yung sagot niya ay naging 3.4? Okay? Bakit yung naging ganon? Kasi, ang log of 2.5 class is 0.4. Am I making myself clear? Kasi na-shortcut na eh. Yung log of 2.5 is equal to 0.4. Maliwanag po ba? Ngayon, so, class, si Aliyah, okay. Paano yung iba? Okay din ba sa inyo? Nagets nyo po ba yun? Okay. So, yung log ng 2.5 ay 4. 0.4. Ngayon, ima-minus yon sa 4. Kaya, 4 minus 0.4 is equal to 3.6 kanina. Okay? Ngayon,
Minus 4. This will give us a pH value of 3.6, which is indeed between 3 to 4. That will give you a value of 4.4, which is between 4 and 5.
Okay.
Number two, the pOH of the solution is 4.5. Calculate the pH of the solution. So that's another simple question. What formula do we need in order to calculate the pH given the pOH? So here's the next equation that you want to write. You should add it to your list of equations for acids and bases. The pH plus the pOH of a solution must add to 14, especially at 25 degrees Celsius, because Kw, the auto ionization constant of water, is 1 times 10 to the minus 14. So to calculate the pH, it's simply going to be 14 minus the pOH. And so that's going to be 14 minus 4.5. Now 14 minus 4 is 10, and 10 minus 0.5 is 9.5. So this is the pH of the solution. Now here's a question for you. At 25 degrees Celsius, would you say this solution is acidic, basic, or neutral? What would you say? Now, it's important to understand that if the pH is less than 7, we have an acidic solution. If the pH is equal to 7 at 25 degrees Celsius, the solution is neutral. But in our example, because the pH is greater than 7, we have a basic solution. So in a basic solution, the amount of hydroxide is greater than the amount of hydronium ions in a solution, if it's basic, which it is. So 9.5 is the answer for this problem. Number 3, if the pOH is 3.8, what is the hydroxide concentration? Now, we know that the pH is equal to the negative log of the hydronium ion concentration. So therefore, it stands to reason that the pOH must be equal to negative log of the hydroxide concentration. So we need to solve for this. So how can we rearrange this equation? Well, let's do a basic review of logs. Let's say if we have log base A of B, which is equal to C. You could change that equation from its logarithmic form to its exponential form by doing this. A raised to the C is equal to B. Now the base of a log is 10. So first we need to move the negative sign to the other side. So negative pOH is equal to log base 10 of the hydroxide concentration. So therefore we can say that 10 raised to the negative pOH is equal to the hydroxide concentration. And so this is the formula that you want to add to your list, because that's what you're going to use to get the hydroxide concentration. So it's 10 raised to the negative 3.8. And so that comes out to be 1.58 times 10 to the minus 4 moles per liter. So that's how you can calculate the hydroxide concentration if you're given the pOH of the solution.
Milky na, chocolatey pa. Yan ang paborito niyang Chucky.
Gently exfoliate with Celotac. Helps make skin look healthy plus rejuvenated.
Number 4. What is the pOH of the solution if the H3O plus concentration is 4.2 times 10 to the minus 3? So go ahead and pause the video and try this if you want to. Now the first thing I recommend doing is calculating the pH.
Okay, class. Why don't you try doing it? What is the pOH of the solution if the concentration is 4.2 times 10 to the minus 3? Let's see. What, do you have your answer with you? May sagot na kayo, anak? Okay, what is the pOH of a solution if the hydronium ion is 4.2 times 10 to the minus 3? Okay, I will give you the logarithmic value of 4.2. The logarithmic value of 4.2 is 6.62. Log 4.2 is equal to 0.62 class. Okay. Now, what will you do with that? Will you add that to 3 or subtract? Since it's a higher than 1, you subtract that with 3. So, 3 minus 0.62. And that is equivalent to 2.38. Okay? And that is the, 2.38. May tanong ba kayo doon, anak? Paano kinuha yung 2.38? Yan ngayon yung pH of the solution. Yan, nasa chat box. 3 minus 0.62 is equal to 2.38, the pH of the solution. May tanong ba kayo dyan? Kasi, bakit po ulit minus sa 3? Kasi anak, 4.2 siya. Mas mataas siya sa 1. Diba? Pagka siya ay 0.42, mas maliit sa 1, saka siya i-add. Anak, nasagot at ba kita, Aliyah? Okay. Okay. Okay, so 2 point, yan. Sabi ni Celio, 2.377 daw. Okay, so kung yun na nakuha mo, let's see sa video kung tama ba yung ating mga nakuha. Sa video kasi 2.377. Okay, so bakit ba? 68. Kasi ang log kasi ng 4.2 ay 6.23. Kaya 377 ang kinuha niya. Okay, nag-round off kasi ako, anak. So, yun. Kaya iba yung sagot ko sa sa video. Tama si Celio, ito yung nakuha. 2.377, nag-round off si ma'am. Is at 0.38, okay? So, sige, tingnan na lang natin. So, the pOH will become, bakit kailangan niya mag-3? Anyway, hindi na ako makikipag-argue kasi dapat dalawang significant figure lang yan. pOH. So, anong mangyayari? Ima-minus mo lang ito sa 14. Okay? Para makuha mo yung pOH.
The pOH is going to be 14 minus the pH of the solution. So that's 14 minus 2.377. And that works out to be 11.623. So that's the pOH of the solution.
Oh, or
Number th-
11.623 o pwede din naman siyang 11.62. Okay. So let's stop there the video. Balikan natin yung ating mga pH ng solution natin. Okay lang ba sa inyo? Balikan natin ha. Sharing this tab instead. So, di ba yung ini-add natin class ay 1, mamaya tayo sa buffer solution anak. Naandito naman kasi yun sa ating ano. Para alam natin yung pH ng ating solution. Ang hirap kasi, hindi ba hindi nagwo-work yung ating pH meter? Okay, balik tayo dito. So, class, ano ang pH ng ating 0.001 molar HCl? Anong ini-expect mo na pH nito? Sige nga, compute nyo nga. Gawin nyo nga yan na ano, na exponential form. Anong exponential form ng 1.001 molar HCl? Ano exponential form yan? Okay. So, ang exponential form yan, class, ay i-move mo to the right. Let us move the decimal place to the right. This one. Ilang beses ko siyang i-move para mapunta sa 1. 1, 2, 3, 4. Tama ba? Para maging ano? 1 times 10 to the minus 4. Yan ang kanyang exponential form. O ngayon, yan na yung ating exponential form. So, ano ngayon ang pH ng ating hydrochloric acid? Anyone? Tama. Hydrochloric acid. 1 times 10 to the minus 4, anak. Anong pH ng ating solution na yon? 4. Very good. 4. Very good. Very good, Aliyah. Very good, Carmela. So, nakuha ba natin yung pH na yon? Sino nakakuha sa inyo ng pH na 4? Parang wala, di ba? Meron siguro. 5 ang nakuha nyo eh. Parang 5 yata yung nakuha. So, dapat pala, ang reading pala dun sa 0.001 molar na HCl ay 4. Ngayon, doon sa 0.00, ilan ba yan? 0.1 na na sodium hydroxide. Ano ang pH niyan? Okay, so diyan ang given sa iyo pag kinuha mo will be the POH. What will now be the pH? Very good, Celio. So yan yung mga pH na dapat nakuha natin na hindi. Sino nakakuha ng 10? Nakita ko 11 na initial. 12, mga ganon. Tama ba? Yon. So those will be the initial pH. So, kung babalikan ko anak yung ating data sheets. Okay? So let's write here 0.00. Wait lang anak ha. So, sa pure water, this is expected to be 7. Wait lang. Magpapalit ako ng presentation na. Wala. Sorry, mali ako. Stop sharing. Ba't ako, sabi ko, wala. Ba't ako naandun? Okay. So, ito kunyari yung data sheet natin. So, pure water, ito yung 0.0001 molar HCl. Itong kabila is 0.0001 molar NaOH. So, ang initial natin sa water dapat 7, tama? Ngayon, sa HCl, ang initial natin ay 4. At ang initial natin sa sodium hydroxide ay 10. Okay, so ito yung mga theoretical value class na ating ine-expect na makikita. Okay. Naipaliwanag ko ba hanggang doon sa initial pH? Kung paano nakuha, anak? Hello po. Clear ba yon? Okay. So, sila lang tatlo ang nagpa-clear. Paano yung iba? Sige, you may ask me na lang on Wednesday regarding this one. Ngayon, nung mag-add tayo, ano yung ini-add natin, class? Ang in-add natin based dun sa procedure ay we added how much? 0.1 ml of 1.0 molar HCl. Okay, so what is the pH of the solution that we added? Okay, that is almost 0 class. However, we just get 0.1 ml. Nung kinompute ko to class, the pH of the solution dapat for the unbuffered one, okay, this one should become, from 4, it should become point, almost 2. Yan yung magiging pH niya. Kasi hindi negligible yung kanyang value. Okay. And then, so from 7, it should almost bababa siya ng mga approximately 4. So medyo tama yung iba dito. 5 yung inilagay ninyo, di ba? Pero 5 din yung pH ng pure water. Ngayon, itong sodium hydroxide, siguro bababa siya ng mga approximately mga 8 or 9. Pwedeng 8 or 9. Okay, hindi ko na to kinompute. Ano na lang to? Kasi magbabalanse pa ako ng mga hydroxide ion concentration. Kaya hindi ko na to kinompute, class, kasi mag-a-add pa ako. Pero approximately, ito yung mga change sa pH niya. Pwedeng this may become higher because there are more sodium hydroxide. Okay? So, Ganon din dito, this will become approximately mga 8 or 9. Ito, pwedeng maging, what did you get here, anak? Kasi magre-react yung hydronium sa POH. So, mga approximately, pwede siyang maging 7. Pero, or higher. Ito, pwedeng maging 12. Now, class, yung panghuli na data na inilagay ko yun sa base at saka sa acid, hindi ko na yun kinompute. Okay? Inassume ko na lang yung mga values na yun na approximately it may be to that end. So, nakita natin na medyo talagang nag-deviate yung ating mga results. Besides, we're also using 1 pH paper. Kaya siguro din hindi natin makuha yung perfect na gusto nating makuha. Okay? Maliwanag na ba yung experiment natin, anak? Nung isang linggo? Nung last Wednesday? Naging maliwanag na ba? Okay. So, yun yung mga posibleng pwedeng nangyari. So, ngayon, let's proceed naman to the buffer solution. So, we watch first how to compute for the buffer solution. Now, remember class, I have mentioned that the acid will dissociate. Okay, and the dissociation constant is equal to hydronium ion concentration, that is H plus your conjugate base. This is our conjugate base. Wait lang. The A minus divided by our acid. So the concentration of hydronium ion multiplied by the concentration of the conjugate base is equal to, divided by the concentration of the weak acid is equal to the Ka or dissociation constant. Now, the equation can be rearranged as follows. Here. So, pwede nating makuha yung H plus, di ba? So, we can derive that and we can get that one as Ka times Ha divided by A minus. Just by rearrange, okay? Now, if we will be able to get the pH of the buffer by getting the pKa plus log of A minus over HA. And this one is known as the Henderson-Hasselbalch equation. Okay, make sure that you remember this equation, the Henderson-Hasselbalch equation. It is derived from the dissociation constant of the acid. From here, we can compute for the weak base and the conjugate base and the weak acid concentration given the pKa of the weak acid. Okay? So, let us watch a video how to compute for the pH of a buffer solution. Okay, class, wait lang. So you get the Ka, the dissociation constant. You write first the product of the equation. So in the product kasi, you will get the ions that are produced when HF dissociates. So you have your H2O plus hydronium ion and the fluoride ion at the denominator. At the numerator, sorry. Okay, maliwanag po ba class? Ang inilalagay natin sa numerator ay yung mga ions na naging na na-produce during the dissociation of the weak acid. Is that clear, class? Is that clear? Ay, oo nga, di na po nakapresent yung video. Thank you. Okay, so we are asked in the problem, what is the pH of a solution that have 0.2 molar HF hydrofluoric acid and 0.1 molar sodium fluoride. And the dissociation constant is 6.3 times 10 to the minus 4. Now first, we will write the equation when the acid dissociate. So HF will dissociate into your hydronium ion and your fluoride ion. Okay? So, in this equation, your dissociation constant is equal to the concentration of your hydronium ion and the concentration of your fluoride ion divided by the hydrogen fluoride, which is your weak acid. Okay? So, this is the ones that affect our dissociation constant, and they are needed to determine also the dissociation constant. Maliwanag na po ba kung paano nakukuha yung dissociation constant? Hello? Anak, okay. Isa-isay natin ha.
So, how do you solve an equilibrium expression like this one? The most common way to do it is with an ice table. I'm going to start with my HF. It creates H3O plus and F minus. But watch this. My initial concentrations of HF are 0.2 and F minus is 0.1. In a lot of weak acid, weak base equilibria, you're going to start with only reactant and you won't have product left. But here, because we're starting with some conjugate base already in solution, our initial concentration of the conjugate base is not 0. The change. Let's assume it goes to the right, minus X for the reactants, plus X for the products, because we're gaining a certain amount that we don't know how much yet. And so my equilibrium concentrations are 0.2 minus X, X, and 0.1 plus X. I'm going to take these equilibrium concentrations and plug them into this equilibrium expression. At the same time, I'm going to use the Ka I was given to plug in here. So, what we end up with is 6.3 times 10 to the negative 4 equals concentration of H3O plus was X, concentration of F minus was 0.1 plus X, concentration of HF 0.2 minus X. Now I'm going to make an assumption, because this is a pretty small number. I'm going to assume that X is small relative to each of these numbers. I'm going to kind of try to cancel them out. We'll see if that assumption holds up later. But now, how do I solve for x? Well, I have to undo division by 0.2. We undo division with multiplication, so I'm going to multiply that by the other side. And we have to undo multiplication by 0.1, so we divide by 0.1. On my calculator, I end up with 6.3 times 10 to the negative 4 times 0.2 divided by 0.1. I end up with, hey, did I do that right? 6.3 times 10 to the negative 4 divided by 0.1 times 0.2. Yeah, I guess I did. X turns out to be 0.00126, which is pretty small relative to 0.1. It's about 1% of it. That's okay with me. I'll leave it there. And so that means that the concentration of H3O plus in the equilibrium solution is 0.00126 moles per liter. Check it out. See how the equilibrium concentration of H3O plus is X? Yeah. So if we want to, we can find the pH by taking the negative log of that number, 0.00126. The negative log of that gives me 2.9. And so the pH of this buffer solution is 2.9. End of story. The key to figuring out the pH of a buffer solution is to use an ice table with an equilibrium concentration, initial concentration that is not 0. Now there's actually an easier way to do buffer calculations. It's called the Henderson-Hasselbalch equation. I'll show you how to use that in a different video, but for now, this is the old school way. Yo, best of luck.
Okay. So you have seen how he calculated the pH of the buffer solution. Okay. So later on, but you will compute for the actual pH of the buffer that we prepared. Okay, but let's continue how to use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation, class, is this one. pH is equal to pKa plus log A minus divided by HA. So it's easy to get the pH here because all you have to do is to get the pKa, and of course the pKa is just the same as getting the pH. It's also log of Ka, okay, plus log of 8a minus divided by HA minus. You should remember this Henderson-Hasselbalch equation. Okay, let us try to calculate that pH of a buffer using the Henderson-Hasselbalch equation.
For buffer calculations, the most important thing to know is the Henderson-Hasselbalch equation. So you need to memorize this equation, and you also need to know how to use it. So the equation is shown here. Our pH is equal to the pKa of the acid plus the log of the amount of base divided by acid. It's really important that you remember this is concentration of base over concentration of acid. So let's take a look at using this equation in a couple of examples. Here's a straightforward example where we need to calculate the pH of a buffer containing 0.1 molar sodium acetate and 0.2 molar acetic acid. So we use the Henderson-Hasselbalch equation. pH is going to be equal to the pKa, which is 4.76, plus the log of the base, so that's our sodium acetate, divided by the amount of acid, that's the acetic acid, 0.2 molar. So our pH equals 4.76 minus 0.30 giving us a pH equal to 4.
Oh, ingatan na.
4.6. So that's all you need to know for this easy example. Now, if you forget whether it's the base or acid that goes on top, you can double check your response by saying if you have twice as much of the acid component as the basic component present, then you know that the final pH should be lower than the pKa. So in this case, we should come up with something that is lower than 4.76, which we did, so that checks out. If you had those reversed, you would have come out with a pH value that was above the pKa. So that's just a little way that you can double check yourself to make sure you put the proper component in the numerator. Another way you can be asked to use the Henderson-Hasselbalch equation is to try to solve for the ratio of this base to acid. So we'll do that sticking with the same sodium acetate acetic acid buffer system. In this case, we know our pH is 5.76. We'll set that equal to our pKa of 4.76 plus log of the base over acid. So we'll subtract the 4.76 from each side. We end up having then a value of 1 equal to log of the base over acid. If you take the anti-log of each side, we end up with a B to A ratio of 10. Remember, that's going to be over that 1 value, so we're going to have a ratio of 10 parts base to every 1 part acid. So if we want to write this way, B to A would be equal to 10 to 1. Let's take a look at another example of how you might be asked to use the Henderson-Hasselbalch equation. In this case, what we're going to do is determine the effect that the addition of sodium hydroxide has on the pH of our buffer. So we'll set this up at the start, just as we've done with the first couple examples. So our pH is going to be equal to the pKa of 4.76 plus log of the base. For now, we'll put in that 0.1 molar sodium acetate divided by acid, which is the 0.2 molar acetic acid. Since we're adding sodium hydroxide, what we're going to be doing is converting the acetic acid into more sodium acetate. So we'll gain that amount to our basic component of the buffer. And when we do that in the process, we'll lose that same amount from the acidic component as it's converted into more of the basic component. So our pH here is going to be equal to 4.76 plus the log of 0.15 over 0.15. So the log of 1 is 0, so our pH is going to be equal to 4.76. What you want to do with these problems is make sure that you're providing the answer for the question that's asked. In this case, we were asked to provide the final pH, so that is 4.76. This also could be rephrased where you're asked to calculate the change in pH. So if that were the case, you would have to know what your original pH is, and for us that 0.1 molar sodium acetate, 0.2 molar acetic acid gave us a pH of 4.46. So if we now have increased to a pH of 4.76, the delta would be equal to 0.3 pH units. So just be careful. Be sure that you read the problems carefully. The last type of problem that we'll look at involves mixing two solutions of different strengths together. So we'll need to use the volumes of each one in order to figure out the number of moles that's present. So in this case, we'll first figure out how many moles of each component are present. So for our base, we have 250 mils of a 0.1 molar sodium phosphate monobasic. So that's going to be 0.25 times the 0.1 gives us 0.025 moles of the base. For our acid, we have 100 mils or 0.1 liters of a 0.2 molar solution. So that gives us 0.02 moles of the acidic component. So our pH is going to be equal to the pKa of 2.125 plus the log of 0.025 over 0.02 moles. So if you plug all that into your calculator, I'm running out of space here, we're going to end up with a pH of 2.22. And if you want to check that, you can just see if we're adding more of the basic component, we should have a pH value that's above 2.125, which we do. So that about wraps up our review of buffers and pH.
Okay, so, okay, class. So, you now have an idea how the pH was, uh, computed for a while lang, anak, ha? Mag-i-screenshot lang ako ng mga present. Kasi there are how many students who are not with us today? In screen. Wala kasi akong tracker eh. Sandali lang. Ayan, dumami na. Kita mo nga naman ano. Okay, class. Sandali. Hindi ko alam kung sino yung dalawang dumagdag. Okay, class. So you have seen how to use the Henderson-Hasselbalch equation in order to compute for the buffer solution. Okay, so that means that we can really also compute for the pH of our buffer solution. Anak, may I go out lang for a while lang? For a while lang. Sige. Please compute while I'm in the comfort room. Why don't you compute, class, the pH of our buffer solution based on the Henderson-Hasselbalch equation? Okay, for a while lang talaga, anak. Call of nature lang. Then we will go on after that one, we will proceed with the effects of temperature on the pH and the pOH. Okay. So, you have here, we prepared this one, the acetate buffer, and then we mix it with our acetic acid. Okay. And our acetic acid, wala pala itong wala pala tong concentration ng glacial acetic acid. Wait lang, anak. So the glacial acetic acid okay. The molarity of glacial acetic acid is 17.4 molar. Okay? So, before you proceed with that, kindly compute for the molarity first of the sodium acetate that we used in the preparation of yun muna. So, 0.40 grams divided by the molar weight of sodium acetate, tapos divided by 0.1. Nako, mahihirapan kayo. Sandali lang, class. Dadating na. Babalik ako. Sabihin na, mahihirapan sila. Okay, class. So, let's compute for the molarity first of our acetate from the sodium acetate buffer. From sodium acetate. Okay. Ah, wait lang anak ha. So for that one class, I will write first the equation. Pero nasulat ko na to sa board. Sandali lang. Wait lang anak ha. Okay. So, our weak acid is CH3COOH, our acetic acid. Okay? That is our weak acid. I will show you later. I will write it first. That will give us, acetic acid will give us H3O plus. Okay. And what? Your weak base, which is CH3COO minus. Okay, di ba? Okay ba, class? Are you with me? Wait lang. Mag-change ako ng ano. Ay, wait lang. Okay. So, saan nanggaling yung CH3COOH natin, class? Nanggaling yan sa glacial acetic acid natin. Acetic acid. Okay? Itong CH3COO minus, saan to nanggaling, class? Saan to nanggaling? Nanggaling ito sa sodium acetate. Okay. Paliitin ko na lang para madali. Oh, wait. So, eto, nanggaling to sa sodium acetate. Mag-insert na lang ako ng text box. Okay, class. Ang tanong ko, saan manggagaling tong H3O plus natin? Analyze muna natin yung problem. Doon sa ating paggawa ng doon sa paggawa natin. Siyempre, manggagaling yun doon sa acetic acid. Okay. So, initially, wala siya. Then, manggagaling yun sa acetic acid. Anong equation ang gagamitin natin for this one? Siyempre, ang gagamitin natin ay ang Henderson-Hasselbalch equation. Ano yung Henderson-Hasselbalch equation, class? pH is equal to so we will be using this one, this equation. Okay? Okay, para makuha natin yung pH ng ating buffer. Alam natin yung pKa, di ba, class? It was mentioned in the video. Okay, kung ayaw mo naman, hanapin na lang natin sa internet yung pKa ng acetate buffer. Okay, the pKa for acetic acid is 4.76. Okay? our pKa is equal to 4.76. Okay, so medyo malinaw na yan. Ano ang concentration ng A- natin, class? Ano ang concentration ng ating CH3COO minus? So this is the equation. And this one's is our given. Okay, so 1. So first, the concentration of our A- is how much did we weigh, class? How much did we weigh? How much sodium acetate did we weigh? Anyone who wants to answer? How much sodium acetate did we weigh last meeting? Naalala nyo ba? 0.4 grams. Okay? Okay? So, weight of sodium sodium acetate is equal to 0.4 grams. So, ilang mole yan? So, how are we going to get the mole from that one? Mole of sodium acetate. We need to get this one. And that is equivalent to 0.4 grams, okay, divided by the molecular weight of sodium acetate is 82. Okay? 82 class. 82. So we will divide this one by 82. Nasa? 82.0 gram per mole. So ang sagot mo ay will be in mole. So and the answer for this one is gahanap ako ng calculator. 0.4 divided by 82.03. Wait lang. Okay, have you computed? That is 0.00487. 0.00487 moles. So that is equivalent to 0.00487 moles. Okay? Now, what is naman, so these are the given, what is the concentration of our acetic acid? So we have 0.3 ml of acetic acid. Okay, now, in this 0.3 ml of acetic acid, we have to get the moles again of the number of moles of acetic acid. So how are we going to get the number of moles of acetic acid? So we need to 0.3 ml, 0.3 ml, and the molarity of our glacial acetic acid is 17. Wait lang, if I am not mistaken. 17.4 molar. And that is equivalent to, wait lang anak ha, magko-compute muna ako. 5.22. 0.3 times 17 teka wala. Wait lang anak. Mali. 0.3 times 17.4 equals 5.22 molar. Moles pala. So using those number, let us substitute what we get. So our equation now will become 4.76 plus the log of 0.00487 divided by 5.22. Sige, i-check ko muna sa aking calculator. Negative 3.3. Okay. I think lalabas kasi dito na yung pH ng ating solution ay magiging aging class. Ang magiging pH ng ating solution ay mag-a-add ka ng 3, aabot siya ng 7.76, which is different from what is stated in our module. Anong nakuha nyo ng pH, anak, para dito sa buffer solution na prepare nyo? 4.7 yung nakuha nyo, ano? 4 yung iba. Yung iba, 5. Tama ba? Okay. So, I think we need to check out our calculation. Bakit, kung saan, bakit hindi pare-parehas yung ating mga 7.6. Mga, bakit hindi parehas yung ating nako-compute na pH as that with our experimental value. Okay, so let's leave it at that. Aking i-aano muna yan, pag-aaralan ko muna bakit hindi. Okay, pero that's how you compute for the pKa of our buffer solution based on the video that we have watched a while ago. Okay, so let's continue. So we have seen that buffer solution should not be affected by any change in pH. Now, how about temperature? How does temperature affects our buffer solution? Okay. In the data, you have seen in the data in the experiment, in the activity, you have seen class that how it, you have seen the trend in the pH as the temperature becomes higher. So what can you say about the relationship of temperature and pH based on the given table? What do you observe when the temperature becomes higher? Anak, yung computation ng ating buffer sa ano ko na lang gagawin ha? Sa Wednesday. O, anong na-observe nyo? Ano yung trend dito sa ating temperature? This is the temperature. Ano nangyayari sa temperature? Anyone? Rain. Kasi si Rain na nakikita ko eh. Rain, anak, ano nangyayari dito sa temperature? What can you say about the temperature, Rain?
Yung sa table po ba?
Oo. Is it going down or going up? You may write
Temperature po yung sa left po or
yung nasa left.
it's increasing po.
Okay, now, what can you say naman with the pH? The one at the right.
It's decreasing po.
So what's the relationship?
As the temperature increases po, the pH decreases.
Okay. So based on the uh based on the data that we have, you will see that as the temperature increases, the pH increases. Now, is it always the case? So let us watch now the video that explained to us the effect of temperature on the pH of a buffer solution. Okay. Okay. You know, class, the pH of a solution is affected by the changes in the temperature. So there will be a change in the concentration also of the substance as the pH, as the temperature increases. Why? Because there will be a higher rate of dissociation if the temperature increases. So now, if that's the case, there will be changes in the values of the ions present in our uh, buffer, and this may affect the buffering capacity of our buffer. So the buffering capacity, as we all know, is the amount of acids and bases that the buffer can accommodate in order not to change its pH. Because there will also come a point na when you add more acid or base or beyond the buffering capacity, the pH of the buffer will change then. Okay? So, kaya kailangan tingnan natin, we need to look into the effect of temperature in the buffering capacity of the pH. Okay, whether it increases the buffering capacity of the pH or it decreases its buffering capacity. Okay, so let us watch this video to determine the effect of temperature and pH.
So in this video, we're going to look at how pH and temperature are related. Now, first of all, we've got a few facts about pH written up the top here. Firstly, this is the formula or the equation that we use to calculate pH. pH is equal to the negative logarithm of the concentration of hydronium ions in a solution. Now over here, we can see that at 25 degrees Celsius, we know that the ionization constant of water is equal to 10 to the negative 14. We know that this ionization constant is equal to the concentration of hydronium multiplied by the concentration of hydroxide. Also, we know that in a neutral solution at 25 degrees Celsius, we have a pH of 7. Now, firstly, what we're going to do is we're going to show how we can work out that the pH of a neutral solution at 25 degrees Celsius is equal to 7. And we're going to do that using this information here and this information here. Now, first of all, what is a neutral solution? Well, a neutral solution is a solution in which the concentration of hydronium is equal to the concentration of hydroxide. And so what that means is that in a neutral solution, if we have a temperature of 25 degrees Celsius, and therefore if our ionization constant is equal to 10 to the negative 14, then we know that at 25 degrees Celsius, the product of hydronium concentration and hydroxide concentration is equal to 10 to the negative 14. Now, because these two things are equal because the concentration of hydronium is equal to the concentration of hydroxide in a neutral solution. If we have a neutral solution at 25 degrees Celsius, then we can say that concentration of hydronium squared is equal to 10 to the negative 14. And therefore from there we can see that concentration of hydronium is equal to 10 to the negative 7. And this is also equal to the concentration of hydroxide. And from there, if we sub 10 to the negative 7 into this equation here, we see that pH is equal to 7. So that's how we can show, using the ionization constant of water, as well as this formula here, that at 25 degrees Celsius, a neutral solution has a pH of 7. Now, how does temperature affect this pH? So that's one process, but now how does temperature affect this? Well, to understand how temperature affects pH, we need to see, first of all, the self-ionization of water. We need to look at this reaction. So the self-ionization of water has a chemical equation that looks like this. So we have two molecules of water producing a hydronium ion and a hydroxide ion. And it so happens that this reaction has a positive change in enthalpy and is therefore endothermic. So this is very important. This reaction here is endothermic, and so that means because it's endothermic, as we increase the temperature, the K value, or the equilibrium constant, increases. Now for this reaction, the equilibrium constant is equal to this expression here. And so if the K value of this reaction here increases, we know that the concentration of water in any sort of solution is very high and pretty much can be treated as a constant because it's so high. And so therefore if our equilibrium constant increases, then that means that the top line of this expression here means that this also increases. So this product on the numerator of our equilibrium constant, this product on the top of this fraction also increases, and we know that this product is equal to the ionization constant of water. So that shows us that when temperature increases, the ionization constant of water also increases. So this number here increases. That means when it's warmer, we have more hydronium ions and more hydroxide ions. So that is what we're dealing with. And so as we heat things up, we have more hydronium ions, and it so happens that if this number in here, this concentration of hydronium ions increases, that causes a decrease in pH. That's how this relationship works. So if the ionization constant goes up, then that means the concentration of hydronium goes up. And that means that the pH goes down. So that is how temperature and pH are related. An increase in temperature causes an increase in the ionization constant of water. That means we have an increase in the hydronium concentration in water, or in any aqueous solution for that matter, and therefore the pH of any solution will be lower at higher temperatures. And so if we have a temperature higher than 25 degrees Celsius, a neutral solution will actually have a pH of less than 7. If we're below 25 degrees Celsius, a neutral solution will have a pH greater than 7. So what we're going to do now is look at an example of that. So what we're going to look at is an example of a temperature, is an example of a solution, a neutral solution, that has been cooled down. So we've got a neutral solution, and our temperature is less than 25 degrees Celsius. We've cooled it below 25 degrees Celsius. And from this relationship here, we can see that if the temperature is below 25 degrees Celsius, then the ionization constant will be below 10 to the negative 14. So this tells us that the ionization constant of water is less than 10 to the negative 14. Now it just turns out that we've actually done some calculations and some tests, and we've been able to figure out the exact ionization constant of water of this solution. And the ionization constant in this case is equal to 0.5 times 10 to the negative 14. It's half what it usually is. So that seems like a really big change. If with our ionization constant, because we've cooled our temperature down, our ionization constant has halved. That seems like a really big change. Okay, so now what we're going to do is figure out the pH of this solution. So it's a neutral solution, but because it's not at 25 degrees Celsius, the pH won't equal 7. So we're going to work out what the pH is equal to. So firstly, we're going to use the fact that because it's neutral, the concentration of hydronium is equal to the concentration of hydroxide. And what that means is that the self-ionization constant of water, we know that Kw is equal to this expression here. And because these two things are equal, we can rewrite this as simply the concentration of hydronium squared. And we know that this is equal to, as we've got written up here, 0.5 times 10 to the negative 14. Now, if we take the square root of both of these numbers here, then we know that concentration of hydronium is equal to the square root of this thing here. And so the square root of this thing here is equal to 7.07 times 10 to the negative 8. So we've put that in our calculator and we've gotten this number here. Now we know that the equation for pH is given by this. So pH is the negative log of the concentration of hydronium, which in this case is 7.07 times 10 to the negative 8. If we plug that into our calculator, we get an answer of 7.15. So although we've cooled down our solution such that the ionization constant has halved, it's reduced by a massive amount, it's halved, our pH of our neutral solution has only increased from 7 to 7.15. It hasn't increased by very much. So we've cooled our solution down, which has caused a decrease in the ionization constant of water. And that has meant that our pH of a neutral solution, and therefore the pH of any solution, is higher than what it would be at 25 degrees Celsius.
Okay, so from that one, you have seen why the pH of the solution decreases when the temperature increases, because the dissociation constant increases also. So you have a greater concentration of your hydronium ion as it increases. Okay, so let us watch the next video. Now, for the next video, it explains to us how the pH, pOH, and pKW is affected by temperature.
Here we'll consider how a change in temperature will affect the pH, pOH, pKW, and neutrality of pure water. We'll just do a quick review of the relationship between hydronium ion concentration and pH. Because this is a negative sign, the pH and the hydronium ion concentration have opposite trends. So as we increase the hydronium ion concentration, the pH decreases. Similarly, when we consider hydroxide ion concentration and pOH, because this is a negative sign, the pOH and the OH minus concentration have opposite trends. So as we increase the hydroxide ion concentration, the pOH decreases. We'll make a note of these up here. Now we'll review how the temperature affects the ionization of pure water. Remember, this equilibrium exists in all samples of water, and it's endothermic. Also recall that increasing the temperature adds heat to this equilibrium system. According to Le Chatelier's principle, the equilibrium will counteract the addition of heat by shifting to the right. As the shift to the right occurs, the hydronium and hydroxide ion concentrations increase. Water is a liquid, so its concentration does not change. After the shift, a new equilibrium is established in which the concentration of
Ay,
H3O and the
ano,
concentration of
mas,
OH
mas,
minus are both
masakit ang
higher
aking
than they
kamay,
were
anak.
before the shift. It is important to
Ay, hindi
realize that when
naman.
the temperature increases, the concentration of hydronium and the concentration of hydroxide
Medyo.
increase by the same amount, and the concentration of hydronium and the concentration of hydroxide remain equal to each other. Therefore, the water remains neutral. So if we increase the temperature and both hydronium and hydroxide ion concentrations increase, as the concentration of hydronium increases, the pH decreases,
Kasi ako eh.
and as the concentration of hydroxide increases, the pOH will also decrease. At this point, you must be really careful. You might mistakenly conclude the decrease in
Kaya,
pH means the
minsan naingat
solution
ako
gets
ngayon.
more acidic. A decrease in
Tama.
pH does not mean the solution gets more acidic.
Ay, oo,
When the
medyo
temperature is
okay.
increased, the concentration of
Okay
hydronium and the
lang.
concentration of hydroxide increase by the same amount, so the water remains neutral. A question we can ask now is what happens to the value of Kw when the temperature is increased? Remember, Kw is defined as the hydronium ion concentration times the hydroxide ion concentration. So as the temperature is increased and the hydronium and hydroxide ion concentrations both increase, so does their product, Kw. Also, as the temperature is increased, the pH and the pOH both decrease. So their sum, the pKw, also decreases. So to summarize, as the temperature increases, the value of Kw also increases. And as the temperature increases, the value of pKw decreases. This makes sense because pKw is the negative log of Kw, so Kw and pKw have opposite trends. And when the temperature increases, Kw increases and pKw decreases. In this table, we'll summarize what happens to each one of these quantities as the temperature is increased and decreased. Because the ionization is endothermic, an increase in temperature causes it to shift to the right. The shift to the right causes the hydronium ion concentration to increase, and the hydroxide ion concentration to increase. Because the concentration of hydronium and the concentration of hydroxide both increase, their product, Kw, also increases. Because the concentration of hydronium increases, the value of pH decreases. And because the concentration of OH minus increases, the value of pOH also decreases. Because pH and pOH both decrease, their sum, pKw, will also decrease. Water remains neutral. Changing temperature alone will never change the acidity of pure water. As long as no acid or base is added, water will always remain neutral. Now, without looking at the answers for increasing the temperature, pause the video and fill in the column for decreasing the temperature on your own. Be able to justify each of your answers. Then resume the video and check your answers.
Okay. So let's try answering. What will happen, class, if the temperature decreases? So what do you think will happen to the hydronium concentration? Anyone? Nag-decrease ang temperature. So what will happen to your hydronium? Yes, Miss Gamil. Ay, hindi ba ano mangyayari, anak? Sino ba? Aliyah, anak. Sige nga, nag-decrease ang temperature, ano mangyayari? Tataas ba ito o bababa? Tataas po. Are you sure, anak? Imaginein mo, pag umiinit, ano nangyayari doon sa ano po? Ano talaga ang gusto mo sabihin, anak? No po. Tataas po, bababa po, magdi-decrease po ba? What do you think will happen if the temperature decreases? So, sige, ibalik natin. Let's go back to the first. Ay, wait lang. Somebody answered. Would it increase po? Sabi ni Rain. Okay, so for us to analyze, anak, sige,
Ionization
let's
is endothermic, a decrease in temperature. Water remains neutral. Changing temperature
here.
alone.
Okay. This is, class, ang bawat chemical equation nagre-respond dyan sa changes in the environment. Okay? Halimbawa, okay, kung dito, para lang pag nagluluto tayo, initially, meron tayong bigas at saka tubig. Ano yung end product natin? Yung kanin, di ba? So, initially, may bigas at tubig ka. Walang apoy pa. There's no change in temperature. Do you have rice already? Cooked rice? Not yet, di ba? Now, what if you add heat? Slowly, what happens to our uncooked rice and water? Slowly, it becomes cooked rice. Okay? Therefore, it shifts towards the product side. Okay? Class, sana naipapaliwanag ko to ng madali. Tama ba? Kasi ganun ang chemical reaction, lalo na doon sa mga reversible. Naaapektuhan siya ng pagdami ng isa at ng init at lamig at pressure. So, nakikita natin ngayon sa screen na when the temperature increases, your H3O also increases because there is a tendency for water to dissociate. Okay? Now, what will happen to hydroxide? It will also increase. Okay? If the temperature increases because the water dissociates into hydronium and hydroxide. Now, if the two concentration degree increases, your Kw will also increase and your pH and pOH will decrease naman because they are inversely related. Okay? So, Rain. If this is the case for the increase in temperature, what do you think will happen when the temperature decreases? Uh, where will the equation go? Will it shifts to the right or to the left?
Ako po ba ulit, miss?
Sige lang, ikaw na.
Would it be to the left po?
Oh, let us see later. Okay. Now, who else? Kasi you're brave enough to answer. I don't want to call those who are not raising their hand. And alam mo yon. Sige. Aliyah, you and Mr. I hope I'm right when I call him Mr. Wait lang, anak. Oh, Celio, anak. What do you think will happen to the hydronium ion concentration if it shifts to the left? Will it increase or will it decrease? Si Hana pa pala, mamaya tatawagin ko. O, based on that analysis, Celio, are you there? Will it increase or decrease? Hala, nagli-leave na sila. Ba't sila nagli-leave? May class ba kayo? Will it increase or decrease, Mr. Besabelia? The one, the only. Group 6. Tama ba, Mr. Besabelia? Are you a member of Group 6? Hala. O sige, si Hana. Hana. Yan. Nasa si Hana. Hana, ano mangyayari sa hydronium ion concentration? Will it increase or decrease? Ay, ayaw na nila sumagot talaga.
Ma'am, for me po, baka po mag-decrease.
Baka mag-decrease. Oh, wala namang wrong or right answer. Kasi sasabihin yan sa atin. Okay, that's a good guess. Same with hydroxide concentration. It will decrease. Why? Because the temperature decreases. So what will happen to the amount of heat? It will decrease. Then the equilibrium concentration or not the equilibrium or the direction of the reaction will now yields towards the formation of water because there is less heat, di ba? Except if, that's also how I see it. Okay. So you're right. See? You got it right. Now, if the what you call this? If the KW decreases, what do you expect will happen to the PKW? Si Celio pala. Celio pala ang pangalan ni Mr. Besabelia. Celio. Okay, how about Aliyah? What will happen to the PKW if it decreases? If the KW decreases? Aliyah? Okay. Sige, you analyze first and you write your answer in our chat box. Si Aliyah sumagot pala siya. Okay, try to write your answer in our chat box, anak. Wala nang gusto sumagot. Decrease din po, sabi ni Hana. So, the PK... Hana, sagot mo ba yan kanina? Increase, sabi ni Carmela. Very good, Carmela. It will increase. Same with your pH and pOH. Okay. So, and your water is still neutral. So, the water did not change its property even if there is an increase or decrease, even if there is a decrease in the H3O plus and OH minus. Bakit? Kasi equal yung decrease sa H3O plus and OH minus or hydroxide. O equal yung decrease sa hydronium at saka sa hydroxide. So, ang tendency class, neutral pa rin yung tubig. Hindi yung bumaba yung isa, mas mababa yung isa. Sabay yung pagbaba ng dalawa and still, the substance is still neutral. Okay?
Now we'll recall the actual values for these in pure water at 25 degrees. The hydronium and hydroxide ion concentrations are both 1 times 10 to the negative 7th molar. The value of Kw is 1 times 10 to the negative 14th. The pH and the pOH are both equal to 7, and pKw is 14. We know that pure water is neutral. Also, the concentration of hydronium is equal to the concentration of hydroxide, which also tells us that it's neutral. Now we'll come up with a range in values for these quantities if the temperature is increased to above 25 degrees. The temperature has been increased, so the ionization of water equilibrium will shift to the right. This would make both the hydronium and hydroxide ion concentrations greater than 1 times 10 to the negative 7. So the product of hydronium and hydroxide ion concentration, Kw, is greater than 1 times 10 to the negative 14th. Because hydronium and hydroxide concentrations are greater than 1 times 10 to the negative 7th, it means that the negative logs of these, the pH and the pOH, will both be less than 7. And the sum of pH and pOH, the pKw, will be less than 14. Because pH is less than 7, you might be tricked into thinking that the water is acidic. But you cannot make this assumption if the water is not at 25 degrees. The hydronium and hydroxide concentrations are still equal to each other, and pure water at any temperature is
That's
neutral.
what I mean.
Changing the temperature cannot make neutral water acidic or basic. We can now quickly determine the ranges of these quantities if the temperature is lowered to less than 25 degrees. Decreasing the temperature to below 25 degrees would cause the ionization equilibrium to shift to the left. This would cause both hydronium and hydroxide ion concentrations to fall below 1 times 10 to the negative 7th molar, and their product Kw would fall below 1 times 10 to the negative 14th. Because the hydronium and hydroxide concentrations are both less than 1 times 10 to the negative 7th, the pH and the pOH are both greater than 7, and their sum pKw is greater than 14. Again, pure water remains neutral, no matter what the temperature is. It's good to be familiar with this table, but instead of memorizing it, it's better to figure out what the values of hydronium ion concentration, hydroxide ion concentration, and Kw will be, just by the way the ionization equilibrium shifts. And to figure out what pH, pOH, and pKw will be, using the fact that they have opposite trends to the hydronium and hydroxide ion concentrations. And of course, remember that pure water is always neutral, no matter what the temperature is.
Okay, so that we have viewed the video on the effect of temperature, we will now go to the activity that you have to answer today. Okay, that will be submitted today, anak-anak ha. So, you have to graph, wala namang pinapagawa. Make a graph presentation of the data, and what can you say about the relationship between pH and temperature? Because all you see is a tabular table, is a tabular form of presenting data. Now you are about to present it in graphical form. Okay. So you have until this evening to submit the graphical uh, presentation of the data on the table. So let us analyze first the data. Now look at the KW as the temperature increases. What can you say about the KW? Class, what happens to it increase po? Kasagot yan ni Carmela. Kanina o ngayon anak? So what do you observe about the KW? It increase. The pH decreases. So it's up for you to make a good. Okay, what will I look into your table? You should have a title. You should have labeled your the graph, labeled the x-axis and the y-axis. Please use Excel. Yun na lang. Para then save your file as PDF. Okay? Text entry of, ano na lang. Save it as a PDF na lang, anak. Okay? Pwede namang isave ang Excel. Marunong ba kayong mag-graph sa Excel, anak? I hope, yes. Yes, very good, very good. So, you may start doing it. You still have 10 minutes to do it. Okay? Yung sa ating buffer solution, medyo iba yung nalabas kasi na value dun sa expected. Kaya I'll start with that maybe on Wednesday. So, on Wednesday, on-site tayo, anak, ha? Okay ba? Okay po ba yon? So, I'll see you on Wednesday. Oo. Para February 14 yon. Happy Valentine's Day, anak. Okay, so start doing your graphs. It's individual. Okay? You should have a title. You should have your label of the variables. Yun lang. Okay, graph, any graph. Bar graph, bar graph, pie graph. Basta just the proper presentation of a graph. Yun lang. Label of the axis. Okay. And the interpretation. The interpretation is very easy because we did analyze the data today. Okay. Are there any questions? Do you have any questions? Class, nalilito ako. Bakit ganito ang presentation ko? Okay, then if you don't have any question, then I'll say goodbye. It's hard to let you go. Okay, goodbye class. I'll see you on
Thank you po.
Wednesday. Thank you.